Hello and welcome to my channel. This is Vivek. Today in this video I am going to discuss about the variable voltage variable frequency drive. Variable voltage variable frequency drive is one of the most efficient methods of starting as well as the speed control of an induction motor. And we will discuss in this video various aspects of the triple VFD, why we use them, what are its characteristics, how it is so much efficient. So we will discuss all of that here. Let's get started. But before we begin, make sure you subscribe to our channel if you haven't already, and do press the bell icon notification button. So in the coming slides, what I'm going to discuss is what is triple VFD. Of course, we are discussing about triple VFD, so we will gain a basic idea about it. Then we will move to previous methods of starting and speed control. As I said, it is one of the best methods of starting and speed control. So definitely we will see what are the other methods, and if they are available, then the question rises that why we are then using triple VFD. Okay. Next, we will talk about the impact of controlling voltage and frequency. As you can see, the name says variable voltage, variable frequency. So we will see what is the impact actually of controlling the voltage and frequency. We will see the characteristic curves of the motor when it is connected to a triple VFD control. And finally, we will talk about the advantage, disadvantage, and we will see some applications of the triple VFD drive. So the first question is, what is triple VFD? Triple VFD is a machine, or you can say a technology that actually controls the VF ratio. Okay, I am coming to what is VF ratio and what is the impact of it. But for now, just see that we control the voltage and frequency in a manner that we get the optimum starting characteristics. Okay, so what is the optimum starting characteristic in any kind of induction motor, whatever be its application? Two most important conditions need to be matched. The first one is the motor should have a high starting torque. Okay, the starting torque of the motor should be high. At the same time, the motor should have a low starting current. Okay, the motor should take low starting current, and both of these criterias are matched by triple VFD, and hence it is one of the most efficient methods of starting an induction motor. Okay, and as we are controlling the F here, so by that we can also control the speed of the motor. I am coming to that, how that happens. For now, let us discuss what are the previous methods of starting and speed control of an induction motor. So, various other methods of starting are there, like we have a DOL start, stator reactor start, auto transformer type start, and star delta starter. For speed control, we have pole changing method, stator voltage control method, rotor resistance control method. So these methods are, so many methods are available for starting and speed control. But the triple VFD gains an edge over all these methods. Okay, I will be coming to that, how that happens. So basically in DOL start, if I start with the starting mechanism, so in DOL start what we do is that we basically connect the motor directly to the line. Hence the name is DOL, that is direct online start. So we connect the three phases of the motor directly to the supply at the supply voltage and supply frequency, and the motor begins to rotate. The next three methods that are there, that is stator reactor start, auto transformer start, and star delta start. Basically in these types of mechanism, what we do is that we reduce the starting voltage. Why we reduce the starting voltage? As the starting current of the motor should be low, so if we reduce the voltage somehow, the starting current will reduce and we will gain the condition of low starting current. If I come to the speed control mechanism, we have pole changing method. Basically what happens in pole changing method is that the speed of a motor, that is the synchronous speed, is given by ns equal to 120f upon p. Right. So if I consider the frequency to be constant, then we have only one thing, that is the number of poles. So by changing the number of poles, by decreasing the number of poles, I can increase the speed, and vice versa. Okay, so that is the pole changing method. In the stator voltage control method, what we do is that we control the voltage so that we can decrease the speed or control the speed. How that works is that the torque of a motor is directly proportional to the slip times voltage square upon the rotor resistance. I am not going to deduce this expression. This is a famous expression of the induction motor. It is the characteristic of an induction motor. So slip times voltage square upon R. As we are controlling the speed and not the torque, therefore we will consider that the torque of the motor remains constant. Okay, so the torque of the motor remains constant, and this is the rotor resistance, which will obviously be constant. So therefore we can say that SV square is equal to constant. Clear? We can say that. So let's say we reduce the voltage. So as the SV square has to keep constant, the S will go up, certainly. If the S goes up, what is the effect? We know that rotor speed is given as NR equal to NS, 1 minus S. So definitely if the slip goes up, this whole factor reduces, and therefore the rotor speed reduces. Okay, so in this way, by controlling the voltage, we control the speed of the motor. So this is the method. And next is the rotor resistance control method, which is basically used in slip ring induction motors. In slip ring induction motor, additional resistors are connected to the rotor conductors. If you want to know why we connect that and what is the difference between slip ring induction motor and the squirrel cage induction motor, you can refer to my video. The link is in the description down below, as well as in the I section in the top right corner. So basically what we are using is that we are using rotor resistance control. So by controlling the resistance of the rotor, we can control the speed. Now the question comes then that if we have so many technologies available, we have so many methods available, then why we are going for triple VFD or something like that? The answer to this is, number one, the disadvantage that we have with the other methods, and number two, the advantages that we have with the triple VFD. Let us first of all discuss about the disadvantages of the other methods. So I start with the DOL start. As you can see in the DOL start, we are directly connecting the motor to the line. So definitely it will draw the same amount of current as it was drawing. And as we know, an induction motor behaves like a short circuited transformer during start. So it will draw a huge amount of current during the start, as well as the motor torque is also very poor. Let us discuss why. So let's say if I am talking about a squirrel cage induction motor, which is basically used in many of the applications. So in squirrel cage induction motor, the rotor looks something like this. There are copper or aluminum bars that are connected between two end rings. Okay. Now let's say you are connecting the motor to the direct line, which means you are supplying it through 440 volt and 50 hertz. Okay, so you have supplied this voltage at this frequency. Now as the supply frequency is 50 hertz, so we can calculate the synchronous speed. Synchronous speed is given by Ns equal to 120 F upon P. So 120 times 50 upon 2. Let's say this is a 2-pole machine. So from here what we will get? We will get 3000 RPM. Okay, 3000 RPM. So the synchronous speed of the motor is 3000 RPM. Let me rub this. So what is the meaning of synchronous speed? Synchronous speed means the speed of the rotating magnetic field. So as we are supplying the motor, what will happen, that a rotating magnetic field will be generated and it will be rotating at 3000 RPM. But at that instant of time, because of moment of inertia, the rotor will not gain any speed, or the rotor speed will be 0. Okay, so at that moment, what the rotor will see, what these conductors will see, that the rotating magnetic field is rotating at a speed of 3000 RPM, whereas the rotor conductors are still at rest. So because of that, as the rotating magnetic field is rotating at such a high speed, it will be cut by these rotor conductors at a very high speed. If these rotor conductors cut this magnetic field at a very high speed, a very high frequency EMF will be induced within the rotor conductors, and because the conductors are short circuited by the end rings, a high frequency current will begin to flow through the rotor conductors. Now as the frequency of the induced EMF is high, what will happen? If I calculate the rotor reactance, it will also be high. Why? Because it is equal to 2 pi FL. So if the frequency of the induced EMF is high, the rotor reactance will go up. And as we know, what is the nature of a reactance? That it makes the current lag by the voltage phasor. So the rotor current that is there, if I denote it by IR, it will lag the voltage phasor V. Okay, and if the rotor current lags the voltage phasor, which means it is also lagging the maximum magnetic field within the machine. Okay, the V and phi m are directly related to each other. I will come to that how that happens, but for now just keep this noted that the maximum magnetic field flux and the rotor current both will go out of phase by 90 degree. So because of the lagging between both of them, the torque during the start of the motor gets reduced. Okay, because if we want maximum torque during start, both the rotor current and the maximum magnetic field flux should be aligned. But as they are not aligning with each other, what is happening? There is an angle of 90 degree between them. So the motor starts with a very poor torque. Okay, so this is the problem with high frequency. We see that with high frequency, the synchronous speed is high. As the synchronous speed is high, the EMF induced within the rotor conductors because of cutting off those high speed rotating magnetic field is that the high frequency EMF is induced, and because of the high frequency EMF, the rotor reactance is high, and therefore the current within the rotor lags the maximum magnetic field flux by almost 90 degree, ideally 90 degree. Okay, if we neglect the rotor resistance. So this is the problem with the DOL start. In the next three, what we are saying that we are reducing the voltage to reduce the current. Okay, one of the objectives we are getting is that the current is reduced, but at the same time the torque also gets reduced. Why? Because as I said, the torque is given by torque is directly proportional to SV square. So if the voltage goes down, okay, SV square upon R, rotor resistance. So if I consider the rotor resistance is constant, of course. So if the voltage goes down, therefore the torque will also go down. So this is the problem with all of these methods that are there. In a speed control method, what is the problem? If I come to pole changing method, then in pole changing method, what we do is that we control the number of poles. So we know that Ns equal to 120F upon P. But there is a limitation of this equation. What is the limitation? The number of poles cannot be reduced beyond 2. Okay, the minimum number of poles that can be there is 2, because magnets have 2 poles, north and south. We cannot make it unipolar. So the number of poles cannot be less than 2. So therefore, as there is a limitation, so by P we can only control the speed up to a certain extent. And if we want higher speed, we cannot reduce the P beyond 2. So this is the problem with the pole changing method. Next we have a stator voltage control method. So in stator voltage control method, the problem is that if the motor is running and at that instant of time you try to control the voltage, the motor current increases, okay, which can burn out the windings. How that happens is that the torque of the motor, as we saw, is directly proportional to SV square upon R, and the current within the motor is directly proportional to SV upon R. Okay, SV upon R. So what happens is that, let's say I reduce the voltage from V1 to V2. Okay, so voltage goes from V1 to V2, and because of the reduction in voltage, we saw that the slip will increase. So let's say the slip goes from S to 2S. Okay, we reduce the voltage, and because of that the slip went from S to 2S, that is the slip doubled. So what is the effect of this? See here, if I put the whole situation in the torque equation, so as I said, in speed control the torque should remain constant, therefore the SV square will remain constant. Okay, which means the torque at voltage V1 will be equal to torque at voltage V2. So what will be the torque at voltage V1? It will be S times V1 square, right? It will be equal to torque at V2 voltage, so it will be 2S times V2 square, right? Now, if I cancel the S on both sides, so what we are getting, that V2 upon V1 is equal to 1 upon root 2. Okay, so this is what we are getting. Now just keep this in mind. Now, if I come to this equation, I equal to SV upon R. So now I will find the current at voltage V1 and voltage V2. So I1 will be equal to, that is at voltage V1, it will be directly proportional to S times V1 upon R. Okay, and I2 will be directly related to 2S times V2 upon R. So if I find I2 upon I1, what it will be? I2 upon I1 will be 2SV2 upon SV1, that is 2V2 upon V1. Right? And what we got is that V2 upon V1 is 1 upon root 2, which means this will be 2 upon root 2. So this will be root 2. So what we are getting finally, that I2 is equal to root 2 times of I1. That is, the current at the reduced voltage is more than the current at the rated voltage. Here we can see that. Okay, so we cannot use the voltage control method. It is not a very good method because it causes the motor to heat, as well as prolonged use of this kind of method can burn out the windings. Similarly, with the rotor resistance control method, as I said that during the start of the motor we connect a set of resistance and because of that what happens? There are ohmic losses. So it is also not an efficient method. So all of these methods, either it be starting or speed control, has some disadvantages. Now, to understand what is the advantage of triple VFD, we have to understand the impact of VF control. And the impact of VF control can only be analyzed properly if we can understand, or if we can know somehow what is the relation between V and F in this situation. So, by Lenz's law, what do we know? That V is equal to, if I write it, so induced voltage V is equal to minus N d phi dt, okay, where phi is the magnetic field flux, okay. Phi is given by, phi is the instantaneous magnetic field flux, so phi is given by phi m sin omega t, phi m sin omega t, clear? So V will come out to be how much? If I calculate it all, it will come out to be omega n phi m cos omega t. Clear? Now, if I want to find Vmax, so when I will get Vmax, we will get Vmax only if cos omega t is equal to 1. So I will put cos omega t equal to 1. So we will get omega n phi m. So Vmax is equal to omega n phi m. Now if I want to find the Vrms, so Vrms or V will be equal to Vmax upon root 2. Okay. So this will be omega n phi m upon root 2. Clear? Because Vmax is omega n phi m. And what is omega? If I write it like this, 2 pi f n phi m. Right? Because omega is equal to 2 pi f upon root 2. So finally, if I calculate 2 pi upon root 2, what I will get is, I will get 4.44. So this equation becomes 4.44 f n phi m. Okay. So now we got this equation that V is equal to 4.44 f n phi m. In any electrical machine, this holds true. However, in rotating machines, we have two more factors, that is Kp and Kd. Kp is known as the pitch factor and Kd is known as the distribution factor. These two are design aspects which come when we try to mitigate the harmonics within an electrical machine. But for now, we consider Kp Kd equal to 1. If you want to know in detail what is pitch factor and distribution factor, you can refer to the videos that I have made on the topic. Okay. But for now, we consider that Kp and Kd is equal to 1. So I will not write it here. So this is the equation that we have. Now we can clearly see that there is a relation between V, F and phi m. That's why I said that if the voltage goes out of phase with the current, that means phi m is also going out of phase with the current in the previous slide. So there is a relation between them. Also, what we are seeing that 4.44 is a constant and n is the number of turns, which is obviously a constant. So the relation becomes V is directly proportional to F and phi m. Or more appropriately, what we can write that V upon F is directly proportional to phi m. Okay. And this is the equation upon which, this is the relation upon which the entire working of the triple VFD is based. Let us see how. So in the previous methods, what we were using for reducing the current, we were reducing the voltage, but in turn we ended up sacrificing our starting torque as well. Okay. But in VF method, what we will be doing is that we will try to keep this phi m constant. And how the phi m will remain constant? Only if the fraction between the voltage and frequency remains constant, only then we can keep the phi m constant. Okay, so I will reduce the voltage and frequency proportionally in such a manner that their fraction remains constant, so that the phi m remains constant. What is the advantage of keeping the phi m constant? The advantage is that upon phi m depends the maximum torque of the machine. Okay, so if I want to start the motor at maximum torque, it is possible with the VF control. So let's say if I am reducing the voltage by a factor X, and I am also reducing the frequency by the same factor, so ultimately the X cancels out and the V upon F fraction remains constant, and therefore the maximum magnetic field flux within the machine remains constant, and therefore the maximum torque remains constant. Another advantage, if you can see, is that we are reducing the voltage during start, but we are also reducing the frequency. What is the impact individually of reducing both of them? By reducing the voltage, we are ensuring that the starting current is low. By reducing the frequency, what we are seeing that the starting torque will be high. Why I am saying like that? Because in the previous slide I showed you how frequency is responsible for poor starting torque of the induction motor. So if I reduce the frequency and I also reduce the voltage, what I will be gaining, that if the frequency gets reduced, the motor will build up its torque. Okay, I can say that let me clear this all. I can say that the starting torque is inversely proportional to frequency, right? So if the frequency gets reduced, the starting torque goes up, right? And if I reduce the voltage, then what I am getting is that the current, the starting current also is reduced. And at the same time, if I am reducing the voltage and frequency in such a manner that their fraction remains constant, so therefore as phi m is directly related to them, so the maximum magnetic field flux within the machine remains constant, and therefore the maximum torque remains unaltered. So this is the advantage of using the VF control method over all the other methods, where we were sacrificing one for getting the another. Here we are getting the high starting torque as well as the low starting current. Now let us move to the characteristic. So under characteristic we will discuss about two conditions. First is below rated speed and second is above rated speed. So we will drive the motor from 0 speed to the rated speed, and from rated speed we will go above the rated speed. Okay, so let us start below the base speed. So if I write below base speed. So how I will control below base speed? So in this scenario, what we will do is that we will keep the V upon F constant, just as I discussed. So I will reduce the voltage and the frequency during start. Okay, so if I reduce the voltage, what will happen? Obviously starting current will be reduced. If I reduce the frequency, what will happen? The starting torque will be high. Okay, starting torque will be high. This is the starting current. So I will start the motor at high torque and with low input current, and at the same time the maximum torque will remain constant. So how it will look like? Let me draw the torque speed characteristic to understand this clearly. So if I draw it like this, so in this direction we have the starting torque, and in this direction we have the speed N, or I can also say F, because frequency, why increasing the frequency increases the speed? Because of this equation 120 F upon P. So initially we were only controlling the P, but now with this technology we will be able to control the frequency as well. I will show you how that happens. Okay, so by controlling the frequency I can increase or decrease the speed now. Okay, so speed and frequency are directly related, so they can be shown on the same axis. Now as I said, the maximum torque remains constant. So let's say this line represents the maximum torque, Tm. Okay. Now I started the motor at reduced voltage and at reduced frequency. So what will be the effect? As the frequency is low, the speed will be low. And at the same time, as the frequency is low, so the starting torque will be high. And as V upon F is constant, therefore the phi m will be constant and the maximum torque will also remain constant. So that's why I have, that is why I have drawn the TM line. Okay, so the starting torque is high and it touches the maximum torque line, and this is the corresponding speed here, N1. Okay, now what I will be doing, that the motor now begins to rotate at the speed N1. Now I will gradually increase the voltage as well as the frequency, because we want the motor to go at the rated speed. So we will gradually increase the voltage up to the rated voltage, and we will gradually increase the frequency as well, so the motor gains the speed. Okay, so now if I increase the frequency, number one, what will happen, the starting torque will go down. So let's say the starting torque goes here. What will be the impact upon the speed? As the frequency has been increased, the motor speed will increase, so it will go here. And what will be the impact upon the maximum torque? It will remain constant, because the V upon F fraction has been kept constant. So this will now go like this. Okay. Similarly, I further increase the voltage and frequency. So again, because of the increase in frequency, the starting torque goes low, the speed increases, and the maximum torque remains constant because of the constant V upon F. So this looks like this. Okay. So let's say this is the point of rated speed. I mark it as NR. Okay. So this is the point of rated speed. So at this point, the motor is at 440 volt and it is at 50 Hertz frequency. So this is the rated speed at which the motor is rotating. So this is the first characteristic where we started the motor from 0 to rated speed. Now I want the motor to go beyond the rated speed, because up to rated speed we can go with various other methods that we saw. So what is the advantage with VFD is that it also allows you to go beyond the rated speed. Let us see how. Now, if I want to go beyond the rated speed, you will say that therefore, okay, no problem, we will increase the voltage and frequency further. But that is not possible. Why? Because we have already attained the rated speed, which means we have already reached the rated voltage. And any voltage increase beyond the rated voltage will result into burnout of the motor or insulation failure. Okay, so in this situation, in this scenario, what we will be doing is that we will keep the voltage fixed, and now we will only increase the frequency. Why? Because 120F upon P we saw. So if the frequency is increased, the speed of the motor will increase. But what will happen further is that because the voltage is fixed and frequency is changing, so phi m is proportional to this. So this will not remain constant anymore. So as phi m is not constant, therefore the maximum torque will also not remain constant and it will vary. Okay. Further, what we are seeing is that we are keeping the voltage fixed and we are increasing the frequency. So overall this fraction will go down. So therefore the maximum torque will go down. Okay. So this is the thing that is there with the VVVfD, is that if we want to increase the speed beyond the rated speed, we can do that by increasing the frequency, but the voltage will be fixed and therefore the maximum torque of the motor will go down. What will be the impact upon the starting torque? The impact upon the starting torque is nothing, but it will go down as well because it is inversely proportional to the frequency. Okay, so how we will draw the characteristic? Let us see. So again I will draw the two axes that are there. So this denotes our starting torque and this denotes the speed ns. And as the NR is dependent upon NS, so if NS increases, obviously the NR will also increase. Now in the previous slide, I showed you that we have already attained the rated speed. Now I want to increase the speed beyond the rated speed. So now, as I said that the maximum torque will not be fixed. Okay, so further increase in frequency will do what? It will decrease the starting torque. So starting torque, let's say, starts from here. And now this is the maximum of the torque. Again, I further increase the frequencies and keeping the voltage constant. So what will happen? The starting torque will go down and the speed will increase, but the maximum torque will decrease. Okay, so the maximum torque will go like this. If I further increase the speed, what will happen? The starting torque will reduce and this maximum torque will go down. Okay. Why the maximum torque is going down? Because it is dependent upon the fraction of V upon F. Okay, so as the voltage is fixed and only frequency is increasing, so V upon F is decreasing overall, and therefore the maximum torque is also decreasing. Okay, if I further increase the F, what will happen? The starting torque will further go down, the maximum torque will also go down, and let me draw it properly. It will look something like this. Okay, and this will be the speed. So you can see that we are gaining the speed, but the starting torque is reducing. However, it is not a problem because the starting torque is required only during start, and we are gaining a high starting torque during the start. So it is not a problem. After starting the motor, the only thing that is required is that it should attain speed gradually. So that's what we are gaining over here. You can see we are gaining the speed in this direction. Okay, the only problem is that after the rated speed, the maximum torque line decreases. If I draw the maximum torque line, so this is the point of maximum torque, this one. Okay, so if I connect the maximum torque points, how it will look like? It will look like this. An average curve will look like this. Okay, now interestingly enough, what we can see is that one motor is there which has the similar torque speed characteristic. That is, if I draw the torque on this line and the speed on this line, so this is the torque speed characteristic, and that is DC series motor. As we know that a DC series motor is one of the best motors for high starting torque, so definitely, interestingly enough, this machine is now exhibiting the nature of the DC series motor. So I can operate in this region by controlling the voltage and frequency properly, and by operating the motor in this region, I can completely get the behavior of a DC series motor. So this is the biggest advantage of the VVVfD drive. Okay, now if I connect the entire thing, how it will look like, let's see. Now this is the torque line, starting torque, and this is the speed ns. Okay, now initially what is happening? Now during the start of the motor, the voltage has been reduced and the frequency has been reduced. Because of the decrease in frequency, the starting torque is high and it attains the maximum torque, but as the frequency is low, so the speed is low. Again we proportionally increase the voltage as well as frequency, so the maximum torque remains constant, but the starting torque is reduced and the speed of the motor increases as the frequency has been increased. I further increase the voltage and frequency. So now what happens? As the frequency has been increased, the starting torque again reduces and the maximum torque is here, and the speed increases. Okay, the speed increases. Now this is the rated speed. After rated speed, what happens? As the motor has achieved the rated voltage, so we keep the voltage constant, and now we only increase the frequency. The V upon F fraction decreases, and because of that, the maximum magnetic field flux phi m decreases and the maximum torque decreases as well. So because of that, this will look something like this now. Okay. Why the starting torque is decreasing? Because of the same thing, that the frequency is increasing, and as the frequency is increasing, so the speed will increase. If I further increase the frequency, keeping the voltage constant, what will happen? The phi m further reduces and the Tm also reduces, and T start also reduces, but the speed increases. Okay, if I further do that, it will look like this. Okay, so this is the overall characteristic that is shown by the motor, which is connected to VVVfD. Okay, so here the torque, maximum torque remains constant. This is the point of base speed, and from here the maximum torque goes like this. So this is the overall torque speed characteristic of the induction motor. Now, so this is the model of a VVVfD drive. It is also called volt per hertz drive. Okay, because we basically control the V upon F by this machine, so it is also called volt per hertz drive. So various components are there. There are three sections. You can see this is called the rectification section, this is filtering section, and this is the inverter. Okay, so by rectification section, what we do is that we connect three-phase AC lines over here, and because as it is connected to rectifier, so the AC is rectified into DC. This rectified DC is then taken to the filtering section, where this pulsating DC is converted into linear DC, and finally it goes to the inverter section. Now in the inverter section, the DC is again converted into AC. So initially we are converting the AC into DC, and again finally at the output what we are doing, we are again converting the DC into AC. So the question comes that what is the advantage of the entire thing? The advantage is that we are now, with the help of this inverter, be able to control the voltage and frequency which we were talking about. How? Let us see. So there are 6 IGBTs in an inverter, as you know. There are 6 IGBTs. So all of these 6 IGBTs, the gate terminal of these IGBTs are connected to a microprocessor. Okay. This 6 IGBTs gate terminal is connected to a microprocessor. What is the work of the microprocessor? To appropriately give gate pulse to these IGBTs. Because you know that IGBT operates when the gate pulse is high. So at appropriate instant of time, the microprocessor decides the time and gives the gate pulse. Now what is the advantage? The advantage is that, let's say if I want to decrease the voltage and frequency, so what I will do is that I will delay the pulse timing. If I delay the pulse timing, what will happen? Less number of pulse will appear in 1 second. If there are less number of pulses appearing at the gate terminal, so because of that we know that the average voltage output from the inverter that is going inside this induction motor, okay, so the average voltage will go down. Okay, so we have lowered the voltage as there are lesser number of pulse appearing in 1 second. So because of that, the output voltage that is going into the motor from these switches, that will be also appearing at delayed time. So that means the frequency will also go down, right? So here you can see that we are now able to control the voltage and frequency by just controlling the gate timing of these IGBTs. Okay, so this is done by the microprocessor. If I want to increase the voltage and frequency, so what I will do is that I will reduce the timing of the gate pulse that is appearing at the gate terminal. So because of that, there are more number of pulse appearing in 1 second, and therefore the average voltage output from the inverter which is going into the induction motor increases, as well as the frequency also goes up because now more number of pulse are appearing at the gate terminal. So these IGBTs will now switch at greater frequency, and because of that the supply frequency to the motor will also go up. So this is the basic theory upon which the triple VFD works. There are 2 types of triple VFD. One is open loop control system, second is closed loop control system. Okay, so in closed loop this whole thing is automatic. Okay, so in most of the application we use the closed loop, but we can also have an open loop system. Now let us look at the advantages and disadvantages of the triple VFD. So we discussed what are the advantages. We obviously know that it helps the motor to start at high starting torque and low starting current. Okay, we saw that. Second thing is it gives us a smooth and wide range of speed control. Smooth speed control. Third thing is obviously we were able to achieve speed more than the base speed. Okay, we were able to achieve that more than base speed. And the last thing is that the entire process was really efficient. So we didn't sacrifice one for getting the another, which was the case in the previous methods. Okay, so there was no such heat loss in the motor. There was no such problem in the motor. What are the disadvantages? First disadvantage is, as you can see, there are a lot of components connected in a triple VFD. This is just a model diagram. In an actual circuit, there are more number of elements that are connected in the triple VFD. So that is a disadvantage, that there are too many components and hence it is a complex system. Okay, it is complex. Second thing is obviously it is costly, because any efficient thing has a cost. Right. Third thing, it requires frequent maintenance, because let's say these IGBTs that are there, they burn out frequently. So proper maintenance is required every now and then. So these are the advantages and disadvantages of a triple VFD. However, it depends upon your application. If the application is really sensitive, then the triple VFD is must. Now, if I talk about the applications, there are a variety of applications. One common application that we know is inverter based AC. Okay, air conditioner. So in inverter fed AC, we know something called inverter. This inverter is nothing but the triple VFD. Now, if I in short describe the entire working of the triple VFD here, so what it does is that, let's say the room temperature is 25 degrees Celsius and you set the AC to 20 degrees Celsius. Okay. So this room temperature will be sensed by a temperature sensor, and this is the temperature that you have set in your AC. So there is a temperature difference of 5 degrees Celsius. This 5 degrees Celsius is called the error signal. This signal will be sent to the microprocessor. We were talking about the microprocessor. The microprocessor will get this data, and based upon that it will generate the gate pulse. Okay, so as the difference is more, so it will generate more number of pulses. As the pulses increase, so what will happen? The voltage and frequency at the motor terminal will increase, and therefore the speed of the motor will increase. Okay, this motor is nothing but the compressor motor, so the speed of the compressor will increase. If the compressor speed increases, what happens? The room cools down. And let's say now the temperature of the room has gone from 25 degrees Celsius to 22 degrees Celsius. So the room temperature is now 22 degrees Celsius, but the set point is 20 degrees Celsius. So now the difference is only 2 degrees Celsius. So corresponding to 2 degrees Celsius, this will be fed to the microprocessor obviously. So corresponding to this 2 degrees Celsius, the microprocessor will again generate this gate pulse. Okay. So it will again, let me clear this. So corresponding to 2 degrees Celsius, this 2 degrees Celsius the error will be fed to the microprocessor, and the microprocessor will again generate gate pulses. Okay, but now it will not generate that much amount of gate pulse as it was generating during the 5 degrees Celsius. Now it will generate a somewhat delayed pulse like this. So because of that, the voltage and frequency across the motor will now slightly go down, because now the error is not 5 degrees Celsius, it is only 2 degrees Celsius. So even if the motor rotates at a lower speed, it will be able to now cool down to 20 degrees Celsius in normal way. Okay, because initially the error was large, so the voltage and frequency had to be great. Now as the error is small, so the voltage and frequency need to be lowered down. So by that the microprocessor in the inverter controls the gate pulse, and by that we are able to control the voltage and frequency. The advantage is that by controlling the voltage and frequency, it is controlling the speed of the compressor, and therefore it is also saving the electric bill. Okay, that is the monthly electric bill. So this is the main advantage with the triple VFD-fed induction motor drive. Other type of application is, of course, we use it in escalators. Okay, we use it in escalators. Cranes are there in which triple VFD is used. Also traction motors, that is in railways. Nowadays this triple VFD drive is used with the induction motor to control the voltage and frequency, to control the speed of the motor and gain a good starting characteristic. So this is all about triple VFD. Thank you very much for watching. If you have liked this video, do press the like button, share this video with your friends, and if you have any suggestion, feedback, query that you want to share with us, the comment section is open, you can put it there. And don't forget to subscribe to the channel and do press the bell icon to receive the notification of every single video that I am making. This is Vivek Choubey, and I will see you next time.